In the previous video, we introduced analysis of algorithm with a simple example, sum of natural numbers. When we were discussing this example, we saw three different solutions. We took their examples and we shown graphs comparing time taken in terms of input size. One thing that we learned in the previous video was we talk about n greater than equal to 0. We talk about time taken greater than equal to 0. So when we are talking about two functions and fn and gn, and if we are comparing their order of growth, we assume that fn is greater than 0 and fn and gn, they both are also greater than equal to 0, right? These are some assumptions that we make. We took some example functions like C1 and C2n plus C3, and we saw that after certain value of n, the C1 was always going to take less time. So the basic idea of analysis of algorithm, the main idea is to measure order of growth of time taken by algorithms. That's the main idea that we use. However, this has some limitations. If you remember the previous example, when we were comparing 1000 with n plus 1, say an algorithm takes 1000 instructions or 1000 unit of time, and there is another algorithm that takes n plus 1 unit of time. This 1000 may be higher because this is probably implemented in a programming language that takes more time, and maybe it's running on a machine which is slower, but it takes 1000 units of time. And we saw that when n becomes greater than 999, then only this algorithm starts taking less time compared to this algorithm. Now imagine an environment where your n never reaches more than 999. When you were comparing your program, which was constant, with your friend's program, suppose it never happens that input size goes beyond 999, right? So that's a limitation of this order of growth analysis. We always talk about limit n tends to infinity. We always talk about that, right? However, in practically, it might never reach that limit, right? It might never reach that high value 999. But that's what we talk about. We talk about only large input size in this theoretical analysis. That's what everybody does when we analyze algorithms theoretically. Let us now talk about order of growth. Order of growth is the main criteria when we do theoretical analysis of algorithms. The idea is simple. If order of growth of the function which represents time taken by an algorithm is more compared to another algorithm, then we say that this algorithm is a bad algorithm. So fn, if said to be having higher order of growth than gn, if limit n tends to infinite, fn divided by gn becomes infinite. And higher order of growth means we say the algorithm whose time is represented by fn is a bad algorithm, right? So if fn represents a bad algorithm, then fn by gn for n tends to infinite would be infinite. Or gn by fn for n tends to infinite is going to be 0. So I'm going to use this expression here, this expression to prove that order of growth of fn is higher. I've taken this example, n square plus n plus 5 and 2n plus 5, and I'm going to use this expression to show that fn is growing faster. And please remember, all this discussion is under these assumptions. First quadrant, right, of 2D coordinate system, where n is 0, n is greater than equal to 0, and fn and gn are also greater than equal to 0. They are mainly positive functions. So let's compute the value of this expression, fn divided by gn divided by fn when n tends to infinite. So we have 2n plus 5 divided by n square plus n plus 6, and we are talking about limit n tends to infinite. So when we talk about order of growth, we always talk about n tends to infinite, although it might not be a practical idea, as we saw in the previous video when we were talking about fun1 and fun2, and we saw that fun1 was having less value only when n was greater than 999, right? and in practical situation it might happen that your input never reaches more than this value, right? But that is fine because it's theoretical analysis, and that's what we do here, right? So let's talk about this expression value. The simple idea to compare order of growth of two functions and get the value of this: take the highest order term and divide it by both numerator and denominator. Highest growing term. Highest growing term is n square. So we divide both numerator and denominator by n square, and what do we get? 2 divided by n plus 5 divided by n square divided by 1 plus 1 by n plus 6 by n square. Now when n tends to infinite, what this value is going to be? When you have n in denominator, all those terms are going to be 0 when n tends to infinite, right? So this is going to be 0, this is going to be 0, and this is going to be 1 plus 0 plus 0. So what is this value? This value is 0, right? 0 divided by 1 is equal to 0. So you get the value 0. You get the value of this expression Gn by Fn is 0. And this is the required condition to prove that Fn is growing faster than Gn, right? So order of growth of Fn is faster than Gn. So if Fn represents time complexity of an algorithm and Gn also represents time complexity of another algorithm, then we say Gn is a better algorithm. There is a direct way to compare order of growth of two functions. In fact, there is a direct way to find out order of growth of any function. Under the conditions, when n tends to infinite, and we are talking about first quadrant, n greater than or equal to 0, and that function is also positive. Under these conditions, we can quickly find out order of growth of any function, and we can quickly compare these order of growth. The idea is simple. Given a function, we ignore the lower order terms, we ignore the leading constants. Now, how do we decide which terms are lower order terms? We must kind of remember this thing, that constant is the lowest growing thing. It never actually grows, it remains constant. Log n grows faster than constant, then log n, then n raised to the power 1 by 3, then half, then n square, n cube, n4, 2 raised to the power n raised to the power n. These are the commonly seen terms in algorithms. Now we talked about ignoring lower order constants, ignoring leading constants, and then how do we decide which one is lower? Let's do some examples. Say I have a function f1 whose value is 2n square plus n plus 6, and I have another function gn whose value is 100n plus 3. Now how do you decide which one is better or which one is faster growing? You ignore the lower order terms of both the functions. So from here you can refer n square is higher order term. So you can ignore n here, right? You can ignore 6 here. And you can ignore the leading constant. You can ignore this constant too. So you say that Fn's order of growth is n square. And what about Gn? You can ignore the lower order term, which is a constant. You can ignore leading constant. And you can say Gn order of growth is linear. And now if there are two algorithms and they have these times taken by them, then you definitely say that Gn is better because n is less than n square. The time taken by Gn is going to grow slow when n grows, and we are talking about n tends to infinite. So that's the general idea, the direct way to find out the order of growth. Ignore the lower order terms, ignore the leading constants, and find out the order of growth and simply compare them. And how do you decide which terms are lower order? You can use this, and the same thing you use to decide which is having better order of growth in these finally found order of growth. Let us do some exercise to find out order of growth of functions and compare them. Say you have Fn as c1 log n plus c2 and Gn as c3n plus c4 log n plus c5. These C1, C2, C3, C4, C5, they are machine specific constants, right? So they are doing some addition, subtraction in your algorithm, and we just put the constants in place of them. Now, which one is growing faster? Please pause this video, find out the order of growth of both the functions, then compare them. So you can ignore the lower order terms in here. C2 can be ignored. Leading constant can be ignored. So you get the order of growth as log n. Which one is lower order term here? This one, because this comes before n. So you can ignore it. You can ignore it. And you can ignore the leading constant. So the order of growth of this function is n. Now, which algorithm is better? This algorithm or this algorithm? So this algorithm is definitely better because its order of growth is less. It grows logarithmically. Let us do one more exercise. C1n square plus C3 plus C4, C5 n log n plus C6 plus C7. What is the order of growth of this function? We ignore the lower order terms, ignore the leading constant, we get n square. What is the order of growth of this function? Ignore the lower order terms, ignore the leading constant, n log n. Now, which one is faster or which one is having less order of growth? See, we can simply cancel one n with the other n and we get here n extra, and here we get log n extra. So n is definitely more from this and this. So we say this algorithm is faster, right? It's going to grow slow, and we can say order of growth of this algorithm is more, right? So this algorithm should be preferred when you have two algorithms with these times. In this video, we talked about order of growth of functions, which was some mathematics that we did. In the next video, we are going to talk about mathematical functions. We call them asymptotic notations, which are used to represent order of growth of functions, which are used to compare order of growth of functions.